So in this video we're going to look at the time of flight mass spectrometer and how it works and how we identify elements and calculate relative atomic mass from mass spectroscopy data. So in the previous video we looked at relative atomic mass, so hopefully you remember that relative atomic mass is the weighted average mass of all the isotopes of an element relative to 1/12 the mass of one atom of carbon-12. Okay, so how do we actually work out how much the abundance of the isotopes? So for example, if you look at, say, boron, I think it is boron, has got a relative atomic mass of 10.8. Okay, so there's two isotopes of boron. There's the heavier one, boron 11, and there is boron 10. So what you could do, you get a sample of boron, you could put it into a mass spectrometer, and it would tell you that you had 80% of this one and 20% of this one. You could then use that data to work out the relative atomic mass. I've just spotted a formatting error. It should read carbon-12, so the 12 is at the top left-hand corner of the carbon, symbolizing it's the mass. So there were a number of different types of mass spectrometers. The one you have to learn about is the time of flight mass spectrometer. Previously, for the last 10 years, it's been a different type, so I'll briefly go through both. So for both of them, you have to have an ionization step. So what happens in the time of flight one, it's this charged needle. So the sample is injected in and the positively charged needle removes electrons and forms positive ions. So the next step is acceleration. The positive ions are attracted to a negatively charged plate and accelerated into a beam. The lighter ions move with a faster velocity, so hit the detector first. The heavier ions move slower, so that's why it's time of flight. At the detector, the positive ions hit the detector, they pick up an electron and form a neutral atom. So then another electron moves to take the place of the one that's being picked up. So this creates a movement of electrons, a flow of current otherwise. The flow of current can be measured, and then you can work out the abundance. You might find out, if this was the boron, you might find out that you had 20% of the lighter one compared to 80% of the heavier one. So I found it quite hard to find a decent diagram of time of flight mass spectrometry. So here's one I drew. So we've got this thin needle, so you've got your sample being ejected. You can see the thin needle is positively charged, so it removes electrons. Here you can see the sample along with the solvent, positively charged. This starts to separate until we got these positive ions like separated. So in this case we're sort of talking about these are different isotopes. You've got the smaller isotope and the larger isotope. They're then accelerated here by the negatively charged plate into a beam, and you can see that the small isotopes are moving faster than the large isotopes. You've then got your detector here, and this is where the electrons are picked up, forming neutral atoms, and you can measure the flow of electrons, which is a current. I'm just going to go through the old mass spectrometer that was in the old spec, because you'll see all these past paper questions on it, and eventually you'll probably wonder how it works. So what happened before? You had ionization as before, but it was slightly different. In ionization, it was a beam of high energy electrons turning the sample into positive ions. They were again accelerated by, again, negatively charged electric plates. So they came into this part and they hit the wall. So what you do is you turn on your electromagnet, and the electromagnet, because these are positively charged ions, the electromagnet deflects them. So the lighter ones would be deflected the most, and they would hit the detector, and you could measure, again using the same method as before with the picking up of electrons, you could measure the abundance of the lighter one. You could then increase the field strength of the electromagnet, and then the heavier ones would start hitting a detector, and you could then measure the abundance of those ones. So similar methods. I think this is the older style one. This is quite big. This is like a few meters long, whereas the new time of flight mass spectrometry works. You can make it quite small. You can just take a look at this slide. It just repeats what I've just been saying. So pause the video. So this shows the mass spectra of boron. You can see we've got two peaks, one at 10 and one at 11. And this is the MZ. So what is the MZ? So Z stands for charge. So most of the ions have lost one electron, so have a charge of 1. So Z is generally just 1. M stands for the mass. So if this boron has a mass of 10, and Z equals 1, then it will have an MZ value of 10. So you can think of these as essentially being the mass. Okay, so this, you can see that it's got two peaks. You've got one which is of higher abundance. You can see this one has a lot more than this one. If you look at this spectra here for zirconium, you can see that it's got 5 peaks, so therefore there are 5 isotopes of zirconium, with the lightest one with an MZ value of 90 being the most abundant. Chlorine, you can see, has got these 2 peaks, and you can see the lighter one again is more abundant. So in this slide, we're going to work out the relative atomic mass for boron using the mass spectra. Okay, so this is what you do. Relative atomic mass is the weighted average. So we want the weighted average of both the isotopes. So what we do is we calculate the abundance of each isotope. Okay. And we multiply the abundance by the mass. So we can see that this has got an abundance of around 20 something, so we times that by its mass. We add that onto the abundance of this, which is around 100, times its mass of 11. So the calculation is shown here. 10 times for 23 plus 11 times 100. Then you divide that by the total abundance. So the total abundance is 123. That's the 23 plus the 100. So you get 1,330 divided by 123, and it comes up as 10.8, which is your relative atomic mass. If you pause the video and have a go at this one, I've given you the abundances. As you can see, there's 5 isotopes. You can see their different MZ values, which is equivalent to the mass. You can see their abundances, so just do the steps that we did before. So what you should have done, taken the abundances, times them by the MZ values, added them all together, and then divide by the total amounts. So the total amount was 100. Let's move the screen down a bit. And you should have got a relative atomic mass of 91.32. Okay, here's the mass spectra you would expect to find of chlorine. It's got 2 isotopes, the lighter one at 3,5, the heavier one at 3,7. In reality, this is what you actually get. So we've actually got a few more peaks. So we've got these 3 peaks here higher up. So these are due to the fact that chlorine exists as a diatomic molecule. It exists as Cl joined to Cl. So the peaks down here are when these have split up into atoms, or ions even. The peaks here are when it hasn't split up. And the reason we have 3 peaks is because, well, we have different versions of chlorine. So for example, the lighter peak, the one at 70, both the chlorines are going to be chlorine 35s. Whereas the heavier one here, both are going to be the heavy version 37. The one in the middle, this peak here, we're going to have one chlorine is going to be chlorine 35, and it's going to be attached to another chlorine, which will be chlorine 37. So a couple more definitions for you. So relative molecular mass, given the symbol Mr, is the average mass of a molecule relative to 1/12 the mass of one atom of carbon-12. So this, to work out the relative molecular mass, you just add up all the relative atomic masses of the atoms in the molecule. Relative formula mass, also given the same symbol, is the average mass of a compound relative to 1/12 the mass of one atom of carbon-12. So you can use mass spectrometry to work out the relative formula mass or relative molecular mass. So in this example, we've put in octane into the mass spectrometer. What you can see has happened is you've got a number of peaks. These peaks are due to the fact that octane is actually split up. Later in the course we look at interpreting these peaks here, but right now we're just going to consider this peak which is furthest to the right. It's called the molecular ion, and it's the peak which corresponds to this not being split up, so the full unsplit up version of it minus an electron. So the molecular ion has an MZ value which is equal to the relative formula mass of the compound. So this is really useful as we can use it to try and identify or help identify what the compound or molecule is. I'm just going to clarify the difference between the definitions of the compound or a molecule. So a molecule is two or more atoms covalently bonded together. So for example, hydrogen is a molecule because you've got two or more, they're the same but they're covalently bonded. Water is another molecule. A compound is two or more different atoms bonded together, but they don't have to be covalently bonded this time. So for example, this isn't a compound because they're not different atoms, whereas water is a compound, it's also a molecule. Something like sodium chloride, there's no covalent bonds here, so it's not a molecule, but it is two or more different atoms, so therefore it is a compound. So if I told you that this was an alkane, you could actually work out which alkane it was. You should know from GCSE that the general formula for an alkane is CnH2n plus 2. So all you have to do is just put in various values for n until you get the total sort of relative molecular mass of 142. So for example, if I try and put in the number 5, so n equals 5, that means I've got 5 carbons. Carbons each have a relative atomic mass of 12, so that's 5 times 12, which is 60, plus the hydrogens. So hydrogens each have a relative atomic mass of 1, so times, that's 10, 12, so it would be 12, so that would equal 72 in total, which isn't enough. If I tried to put in the number 10, then it would come up to 142. So this tells me that this is C10H22, which is decane. So I suggest you now go on to alevelchemistry.co.uk, go on to AQA, go to Unit 1, find exercise 1.1, exercise 2, and try these questions. The answers are also on the website. So in this lesson we looked at how time-of-flight mass spectrometers work. We looked at identifying elements and calculating relative atomic mass from the mass spectra. And we looked at relative formula mass of compounds, also getting this information from the mass spectra.